These next three examples takes advantage of the idea of composition of continuous functions are also continuous. And what this theorem will actually say is that if you know it's continuous at g of a, then the composition f composed with g is also continuous at a. The result can be written as such. We're going to take advantage of this result and use the knowledge of algebra and trig to evaluate the following limits. The idea is to actually look at the inside function first. F composed with g, that means the inside function is actually g of x. G of x function actually goes first. So when you're analyzing the composition of functions, what you're really doing is just analyzing their respective graphs one at a time. So for the very first example here, we could actually look at the inverse tangent, which is the outside function, but we're going to evaluate it with this idea of a limit for the inside function. And if you analyze this one step at a time, you're going to realize as x approaches infinity, where do the corresponding y values go? The corresponding y values are getting very large. Now, how would you write the evaluation for the next line? You have to be very careful. You have to write this with limit notation. As the new x values are getting very large, we're now analyzing this function here, the inverse tangent of x. Notice these values here became these values over here. And so now you just take advantage of your knowledge of trigonometry. What happens as x gets very large? Where do the corresponding inverse tangent values go? Well, they're actually approaching a number, a finite number called pi over 2. So there you go. That's how you determine the limit of this first example. We're going to do a similar analysis with the second example. We're going to look at the inside function first. What happens as x approaches pi from the left? Where do the corresponding y values go? They're actually going to 0 from the right. So once again, the writing is quite sophisticated. We're going to take the natural log and we're going to put this limit as x approaches pi from the left. Where do the corresponding sine of x values go? Let's do that again. As x approaches pi from the left, where do the corresponding y values go? They're approaching 0 from the right. And what are we going to evaluate next? Is actually the natural log function. As x approaches 0 from the right, where do the corresponding natural log values go? They're going to negative infinity. In other words, this limit actually does not exist, but we could still analyze such an expression using graphs. Remember, infinity is not a finite number, so it's okay to write does not exist. We're going to do a similar approach with this last example. We're going to look at the inside function first and see what this will actually become. So as x approaches pi over 2, or I should say negative pi over 2, from the right-hand side, where do the corresponding y values go? They're going to get very large, but in the negative direction. And we know how to evaluate such a limit there. Let's see if this limit exists. As x approaches very large in the negative direction, where do the corresponding y values go? Or where do they approach? They're approaching 0. And so this time the limit does exist. It does reach the finite number called 0. So all these evaluations here just take a very, very careful analysis of their respective graphs.